Hey, math analysis period 1. We're gonna, I decided I wanted to give you a little extra help just to make sure that you got this down. If you had any questions, I went ahead and posted the answer key so you can go back and make sure that you've got the right answers. If you didn't get the right answers, you can use this. I'm just going to be working out some of the solutions right now in this video. And then if the answers still don't make sense, please come join me during office hours to get some one-on-one time with me, okay? So again, this is on page 345 on your review. And I'm just going to pick up where we left off in class. Period 2, we might have done some of these together in class today. We got a little bit ahead of where we ended with period 1. But if this isn't the number that you need, just scroll through and find the number that you want. We're going to start at number 5. It says determine the reference angle. So we're talking about the reference angle, and we're calling it theta prime of the angle at 255 degrees equals theta. Okay? Sketch theta in standard position and label theta prime. So we're going to first sketch this. So if this is 180 degrees, here's 90, here's 0, here's 270. We're going to go ahead and label 255. So I know from standard position, that's starting at 0, to here, we say this is theta. Now, our reference angle, or which we call theta prime. Remember, a reference angle is always to the x-axis. So we're starting at the end, and we're going to draw it up to the x-axis. So this angle right here is what we call theta prime. In order to find theta prime, I just want to know this amount in here. So I can take 255 degrees and subtract it by 180, because I don't really need to know all of this. I just need to know the acute angle, or the reference angle, that's closest to the x-axis. So we get 75 degrees is theta prime. All right, let's do number 6. Number 6 says determine the quadrant. So which quadrant in which theta lies, so where theta is secant theta is less than 0, and tangent theta is greater than 0. So just keep in mind here, they've given us 2 hints. They've told us that secant theta is less than 0 and tangent theta is greater than 0. Just keep in mind, this less than 0, greater than 0 business just tells me that this is going to be negative and this is going to be positive. So what they're saying is some angle where secant is negative and tangent is positive. So we're going to draw our little grid here, and we're going to label ASTC. All students take calc, and that tells us which trig functions are positive in each quadrant. So let's look at this one first. Tangent. I know tangent is going to be positive. First of all, everything is positive in the first quadrant. And tangent is also positive in the... Okay, so we know that tangent, again, is in the first and third quadrant. So let's talk about secant. Where is secant negative? So think about this. Secant is also equivalent to 1 over the cosine function. Because the reciprocal doesn't change positive or negative values, if cosine was negative, secant would also be negative. So we want to know, where is cosine also negative? Well, I know cosine is going to be positive in the first quadrant, positive in the fourth quadrant, but only sine is positive in the second quadrant, so cosine is going to be negative here and also here in the third. So where do both of our hints that tangent is positive and secant is negative, where do they overlap? We see it right here in quadrant 3. So theta has got to be somewhere in quadrant 3. All right, let's do number 7. Number 7 is find 2 exact values of theta. So we need to know 2 exact values of theta where theta is between 0 and 360, and cosine is equal to the negative root 2 of 2. So there's a couple of things here, okay? They've given us a couple hints. The hints are actually within the cosine value. So we know the hint is it's a negative value and that the value is root 2 over 2. This here just tells us that we're not going to go into a negative value of theta or above the 360 degree value. So it's just kind of giving us a limitation of what our values could be. So here's what I'm going to do. I'm looking for an angle. So I'm going to use the information that I already know. So remember, we have our common reference angle chart, right? So we've got 30, 45, and 60 degrees, or this is also pi over 6, pi over 4, and pi over 3, where it says easy as 1, 2, 3, 3, 2, 1, all over 2, root, 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 root. And I know that for cosine, an angle is the root of 2 over 2 when the angle is a reference angle of either pi over 4 or 45 degrees. Okay, that's awesome because we know, okay, in our unit circle now, I know at our pi over 4, so here's pi over 4, here's 3 pi over 4, here's 5 pi over 4, and here's 7 pi over 4. So we just went from the entire unit circle all the way down to just 4 different points that it could be. Let's narrow it down even further. Let's figure out where cosine would be negative. So remember, all students take calc. We know cosine is positive in the 4th quadrant, so that's not going to work here. And it's also positive in the 1st quadrant. So we know cosine can be negative in the 2nd and the 3rd quadrants. And those are going to be our 2 values of theta. And instead of the pi over 4, I could have also written this as 45 degrees. So this is 45 degrees. A 45 degree angle here, if this is 180, would tell me that this is going to be 135, and this was going to be 215. So those are our values. 135 degrees for this angle right here, and this is 215 degrees for the angle right here. Both of those values, if I plug them in for cosine, would give me negative root 2 over 2, and you can test it. All right, let's do number 8. So number 8 says use a calc to approximate the 2 values of theta in radians between 0 and 2 pi. So when they tell you this, by the way, they're kind of telling you, this is your hint, that they want it in radians, okay? For which the cosecant theta equals 1.030. Round your answer to 2 decimal places. So remember, if we know that cosecant is equal to 1 over the sine, then we're going to say here, in order to get cosecant to come off, we have to do the inverse. Well, actually, we can change this way first. If cosecant is theta like this, then I can say sine of this angle is going to be 1 over 1.030, right? In this case, we don't have a key in our function to find an inverse cosecant, but in order to solve for theta, we're going to do the opposite of sine, which is the inverse sine. So in your calculator, you're going to hit the second key and the sine key, and that is how we're going to do the inverse sine. So we say theta equals the inverse sine of 1 over 1.030. So plug that into your calculator, and we get, oh, I can't find my calculator. Here we go. Make sure that your mode is, by the way, whatever you want it in. We want ours in radians, so my mode is going to need to be in radians. Make sure you put your mode in radians. Inverse sine of 1 over 1.030, and we get 1.3 3 because we're rounding to the nearest 2 decimal places. We also needed one more value for where it's going to be this. So remember, 1.3 radians. If I want to graph this, is equivalent to, now if I want to turn that into degrees, I'm going to multiply 180 and then divide it by pi. And I get approximately 76.1 degrees. So that's about right here, okay? This is about 1.33 radians. I want to know where else is the cosecant theta equal here. Well, remember we had to talk about it's got to be positive. Sine is positive here, but it's also positive in the second quadrant. So I know if this is theta, our reference angle here could also be theta. So if this is pi radians, and this distance from here to here is 1.33 radians, we have to figure out what this is. So we're going to find this point by saying pi minus 1.33 radians. Just like if it was in degrees, which you could solve it in degrees, we could say 180 minus 76.1 degrees to find the rest. So if we do this in radians, pi minus 1.33, we end up with 1.81 radians. And those are our 2 values of theta. So we say theta equals 1.33 radians and 1.81 radians. Okay? All right, that was number 8. Let's go ahead and do number 9. So number 9 says find the 5 remaining trig functions of theta, given that the cosine of theta is -3/5 and that the sine of theta is greater than 0. So remember, keep in mind, this greater than 0 business just means it's positive, okay? So they're giving us 2 hints here, that they're giving us the cosine function and that the sine of this angle is positive. Okay, so first of all, I need to know where is sine positive but cosine is negative. So we're going to go ahead and plot that out. So let's find out which quadrant theta is going to be in first. So sine we know is positive in the first and second quadrant, right? Because all students take calc. So we know sine's positive in first and second. Where is cosine negative? Well, we know cosine is negative. We'll put this in purple. Cosine is negative in the second and the third. So the second quadrant is where they both work. So we know theta is going to be in this second quadrant. So now that I have that, I'm going to kind of clean it up and give myself some room to work. So now that I know this is going to be where theta is, and we're going to go ahead and use the information they've given us to go ahead and label all these things. Remember, cosine, if I look at so, ka, toa, ka tells me cosine is A over H. So that means this, if this is A and this is H, we can label our triangle. So the adjacent side would be right here at -3, and the hypotenuse side is 5, okay? So I'm looking for this, and I'm looking for the other 5 trig functions. We're looking for sine, cosine, which we know is actually -3/5. We're looking for tangent. We need to find cosecant, secant, and cotangent. And remember, I have those in those order for a reason, because these are next to what their reciprocal functions are, okay? So quickly, let's go ahead and find the 4th side. If you remember Pythagorean triples are 3, 4, 5. They're a perfect number, but we can also use our Pythagorean theorem to find this. So we'd say -3 squared plus b squared equals 5 squared, which is 25. So b squared equals 16. The square root of 16 is 4. So we worked all that out. I'm going to erase some of it so I can give myself some room. And that this is 4. So I know from this angle, this is the opposite side, adjacent side, and hypotenuse side. So now, here we go. Sine is opposite over hypotenuse. That's going to be 4 over 5. Cosecant is the reciprocal of sine, which would be 5 over 4 now. We already know cosine, they gave it to us, so secant is the reciprocal of cosine, so that's going to be negative 5 over 3. And then tangent, we'll put that in green. Tangent is opposite over adjacent, which is 4 over negative 3. So the cotangent is the reciprocal, is negative 3 over 4. So that's number 9. Let's go ahead and do number 10. So number 10 says, sketch the graph of the function. We have g of x equals negative 2 sine x minus pi over 4. Okay, so let's go ahead and break this down. We need to know how things change, what happens where. Okay, so we've got, this is our a value. There's nothing in front of the x, or if I shouldn't say nothing, there's technically a b there, and this is our c value. So a is our amplitude. So our amplitude is 2. Keep in mind that this negative also means that it's going to flip upside down. Okay, so sine typically goes up and then back down, but this time it's going to go upside down. So it's going to go down and then back up. And then for b, nothing changes in the period. So remember, for period, it equals the normal period for sine times 1 over b. But in this case, 1 over 1 is just 1, so it stays the same. And then lastly, we're going to do the value of c, which is our phase shift. And remember, c is tied in with b, so if b is 1, there's nothing to worry about, but it's always c over b. So in this case, it's negative pi over 4 over 1, which is just negative pi over 4, but if it's negative, remember that it goes to the right by pi over 4. So we have a couple things that we need to adjust. We've got a period of 2 pi, which is normal. We're shifting everything to the right by pi over 4, and our amplitude is now 2. So I'm going to go ahead and plot this out. This is our normal x-axis. And here's our y-axis. So typically the middle line, the x-axis, is the center line, and we go up to an amplitude of 1. But in this case, we're moving it up to a 2. So I'm going to give myself little bumpers to remind myself that our amplitude is no longer a 1 anymore. I'm giving myself like a little bumper. And then typically we would end at 2 pi. But keep in mind, everything's shifting to the right, pi over 4. So before, these were our like middle line pieces, our critical values where we had to have those important points where we graphed starting at 0. But now I'm going to go ahead and put this in blue. Everything's shifting to the right by pi over 4. So instead of starting at 0, I'm starting at pi over 4. And then every other important point also shifts over by pi over 4. So this point on the line is going to be 3 pi over 4. Here's 4 pi over 4. Here's 5 pi over 4. Here's 6 pi over 4. 7 pi over 4. And then here's going to be 9 pi over 4. So really now my important points are the ones that I've labeled in blue. And now I'm going to do the pattern with the little adjustment of flipping it upside down. So remember that sine typically looks like this, okay? We're still going to start at 0, but instead of starting at 0, 0, we're moving everything to the right, so it's starting right here at the pi over 2. And then instead of going up to the amplitude, we're going to flip it upside down, and we're going down. So again, we're lining it up with that next critical point that I've kind of lined up for myself on the x-axis. Next one over, back up to 0. Next one over, we're going to go back and go up to the peak, and then finally ending back at that midline. So when I connect my dots, this is what it looks like, which it still looks like sine, but it's going to be, again, flipped upside down and shifted to the right. Also, the amplitude is 2, which is exactly what we saw before. All right, let's graph number 11. So number 11 says, graph f of x equals 1/2 the tangent of 4x. So let's talk about how this is different. So a couple of things, the amplitude is 1/2, which just means for tangent, the bend, instead of being at the value of y equals 1, it's going to be at 1/2. We also see here, there's a b value on here, which changes the period, which tangent, typically the period is pi, but now we're going to multiply it by 1 over b, which is 1 over 4. So now, instead of the period being pi, it's pi over 4, which is much smaller than it was before. So this is going to happen really quick. So remember, tangent, here's our x and y axis. Tangent normally had a period of pi. But instead of having a period pi now, I'm going to say this is a period of pi over 4. And I'm just doubling it pi over 2 so that we can see 2 full periods of this. I know, so the halfway mark is going to be pi over 8, because half of pi over 4 is going to be an 1/8. And then we'll call this 3 pi over 8. Okay, so we've got some critical values, and we'll go ahead and mark our amplitude here. Now keep in mind, if we can't see it in your head, tangent is equal to sine over cosine. So our zeros are where sine is 0. And remember, sine is 0 at 0. So here at 0, I've got my point, okay? And remember, this adjusted period is pi over 4. So every pi over 4, that distance of pi over 4, it's going to come back to that same point. So I know I'm going to come back to 0 at pi over 4, and then again at another pi over 4. Okay, so those are my zeros. And then I know that when cosine is 0, that's going to make it undefined, and that's going to happen right in the middle of these two. So there's an undefined right in between those zeros. Okay, and now I'm ready to go for my tangent function. I know it starts to go up to the right, and it's going to bend at this halfway mark and then go straight from there, and then down to the left, up to the right, down to the left, up to the right, down to the left. And that's how to do number 11. If you're struggling with this, could you pick any values for x, plot them, and find this? Absolutely. The tricky part with that is sometimes it's not always clear where the asymptotes are. All right, let's do number 12. F of x equals 1/2 times the secant of x minus pi. So we're going to look at how this changes as well. We know here's our a value, which is the amplitude, is 1/2. Here, there's a side like that invisible 1, so the period does not change. The period still stays at 2 pi. And then here, this value of c, that's our phase shift. So for our phase shift, remember that it's c over b, which in this case is negative pi over 1, which is negative pi. When it's negative, it's really moving to the right by pi. So we're amplitude is 1/2, the period stays the same at 2 pi, and we're shifting everything over by pi. So let's set up our graph. Okay, so remember, normally we end everything at 2 pi, right? But we're shifting everything to the right by pi. So I'm going to make another 3 pi mark. Here's pi. Actually, I'm going to make it a little bit bigger because that was not cutting it. I didn't like that it wasn't perfectly lined up. Okay, so here's our 3 pi. Keep in mind instead of starting at 0, 0, we're starting at pi, which means that's why we extended it out a little bit longer on the x-axis, so we could go all the way to 3 pi. And then remember, we're going to need to find those halfway marks. So I'm starting at pi, and then here's 3 pi over 2. Here's 5 pi over 2. Okay, so then these right here are going to be our starting point, and then these are our 1, 2, 3, 4 important points before we hit the end of the period, which will be a total of 2 pi, because we know between pi and 3 pi there's a total of 2 pi here. Let's mark our amplitude, which is 1/2 and negative 1/2. And then I think we're ready to go. So let's mark starting at, oh, the other thing is for secant, remember that secant, we have to graph first 1/2 cosine x minus pi. So which is what, we just set up our axes to do that. And so now we're gonna graph the cosine. Remember that cosine starts at the peak. So we're starting at 1/2. And then at our next point, we go down, down, up, up. Okay, so there's our cosine function. If you want to keep going with this, you can finish it off this way like that. Okay, so now though, we're not done because we still have to do the secant. So remember, secant is the reciprocal of the cosine function. So the reciprocal means that wherever our function was 0, which is here and here, the reciprocal of 0 is undefined. So this is where the asymptotes for your cosine function are. And then we go there and then we find our peaks and our valleys, or the maximums and minimums, and these are now the points that we take our inverses from, and it's going to reflect the shape up within the bounds of the asymptotes. And that is what we look like. So the purple function is our 1/2 secant x minus pi. All right, let's do number 13. Now 13, if you noticed in the directions, I actually had to modify that equation a little bit, only because we didn't really do a whole lot with something called horizontal reflections. So I wanted you to change it from negative 2x or minus 2x to positive. So this is the one that we're going to graph instead of a minus. Okay, let's do number 13. I just wanted to call your attention to this right here. I did, if you look in the directions of your assignment, I did have you change this to a plus. And I did that on purpose because we didn't really practice anything about what a minus there would mean. So we're changing that to a plus so that we can graph it. So let's start by rewriting this first so that this x is actually in the front, because we're normally used to seeing something along the lines of like a cosine bx plus c plus d, right? We're used to seeing it in that form. So we're going to put the x first. So we're going to rewrite this as 2 cosine 2x plus pi plus 3. Okay, so let's go ahead and label all the different changes. And this one has many. So we're going to go ahead and say, well, I know that the amplitude is now 2. The period for cosine is normally 2 pi, but we're going to multiply it by 1 over the value of b, which is really 1/2. Okay, so that's pi, 2 pi times 1/2 is pi. And then this phase shift, remember this value of c, we also have to consider c over b, which is in this case pi over 2. So everything's going to be shifted to the left, because if it's positive pi over 2, it's going to the left by pi over 2. And then the last thing we have to look at here is 3, which everything goes up by 3. So we have a lot of changes happening here. So let's go ahead and go through some of that. So if I'm setting up my axes, we have quite a few things that we have to consider. Number 1 is that our x-axis is no longer going to be the center or that midline of our graph. Our amplitude of 2 tells me, or I shouldn't say that, our adding 3, moving everything up 3 is actually going to be our new midline. So this 3 right here is the midline. And actually, you know what? I'm going to move this down because I'm not going to have enough room if I do that. So I'm going to move this up a little bit. Okay, so this is my x-axis. So if I go up 1, 2, 3, this is my new midline. Everything's coming from there. And then we know the amplitude is 2. So that's the farthest up my graph can go is 2 from that midline, which is a 5. And then this is a positive 1, right? So this is going to be like what we talked about, that bumper bowling. So this is as far down as it can go. This is as far up as my graph can go. So I've got my bumpers in there for my amplitude. And then remember that the period changed. The period changed to pi. So, and then remember, we're also saying everything starting to the left by pi over 2. So, ooh, whoops, actually, I need to move this x-axis over a little bit, or the y-axis, I should say, because I need to make room for that shift to the left. So for my y-axis, so if this is, typically we would start at 2 pi, or our period's 2 pi. So there's pi, here's pi over 2, and here's 3 pi over 2. But for us, because the period is pi, we're going to end at pi. But remember, we're shifting everything to the left by pi over 2. So instead of starting at 0, we're starting at negative pi over 2. So then within a period from pi over 2 is going to be my full pattern of the cycle. So I'm going to break up this distance into even spaces. So this is negative pi over 4, and this is positive pi over 4. So now we've got our starting point here at negative pi over 2, and then we have our 4 critical values within a period of what's going on here. So that's how we're going to start this, okay? So now that our x-axis is all set up and our y-axis is set up, now let's go ahead and start graphing. Remember, we're graphing cosine. Cosine, the basic function looks like this. It starts at the peak. So we're going to start on our first point. Instead of starting at 0, we're starting, remember, to the left at pi over 2. So that's left at pi over 2. And we're going to the peak of our amplitude, which is right here. And then our pattern from there is we go down to the midline, down to the bottom of the amplitude boundary, back up to the midline, and then up to the peak. And then we're going to connect our graph. And if we want to keep going with that, we can. But we only have to have one period. So if I want to keep going with that, I can like this. And so on. Okay, that's number 13. Let's do number 14 together. F of x equals 2 cosecant x plus pi over 2. Okay, so again, we're going to go through. Remember, with cosecant first, you need to graph to sine x plus pi over 2, because sine is the reciprocal function of cosecant. So we know the amplitude is 2. There's no change in the period, so the period is still pi over 2. We say no change because it's just a value of 1 for b, and when the value of b is 1, there's no change in the period. And then the phase shift is c over b, which in this case is pi over 2 over 1, which is positive pi over 2, which means we're changing everything and we're going to the left by pi over 2. So let's set up our axis now. Okay, here's our x and y axis. And we know the period's 2 pi, but remember, everything's shifting to the left by negative, or by pi over 2. So instead of starting at 0, we're starting at negative pi over 2. So we're going to need to mark this off. Here's 2 pi. But keep in mind, the period is a full 2 pi. So the distance between starting at negative pi over 2 and 3 pi over 2 is a distance of 2 pi. So we're going to have an entire period within that amount. Our amplitude is 2. So I'm going to go ahead and mark that off for my boundary. That I'm reminding myself that I'm going up to 2, not up to 1, and down to 2, not down to negative 1. All right, so we've got our axes set up, so now we can follow our pattern. Remember that sine typically looks like this, starting at 0. So our first point, we're going to start at 0, which in this case, we're starting at negative pi over 2 because we shifted everything over to the left. And from there, we're going to follow our pattern. So we're going to go up down, down, up. And there is our graph. All right, let's do 15. Last one of graphing. F of x equals 2 cotangent of x minus pi over 2. So again, remember cotangent is like tangent in that it has asymptotes, but it doesn't have like a peaks or valleys like sine and cosine do. These go on forever. We also know typically that cotangent looks a little different than tangent, where tangent goes through zeros, but cotangent goes through the pi over 2 and 3 pi over 2, and its asymptotes are at 0, pi, and 2 pi. And it also goes to the down to the right, up to the left like this. So this is typically what cotangent looks like, but let's see how this is changing. Here's our amplitude at 2. The period is staying the same. Remember, the period of tangent and cotangent is both pi. And our phase shift is going to be negative pi over 2 all over 1, c over b, which is negative pi over 2, which in this case moves everything to the right by pi over 2. So if I'm setting up my axis here, I know this is typically pi, here's 2 pi, but remember everything's getting moved to the right. So here's pi over 2, 3 pi over 2, and 5 pi over 2. And then our amplitude, instead of our bend happening at an amplitude of 1, it's happening at an amplitude of 2. Okay, so remember cotangent at 0 is an asymptote. And so remember everything gets shifted over to the right by pi over 2, so the asymptote is now at pi over 2, okay? And we also know that within a pi, it repeats its value. So from here to here is a pi, so I know my next asymptote was within, because every period it repeats, right? So that means in the middle is where I'm going to find those zeros. Now that I've got my zeros and my asymptotes, I'm going to follow the pattern, which goes down to the right. So we're going to kind of make that bend down to -2. Okay, and then go like this. And we're done. All right, that was number 15. And I think we're going to do number 18 now. Number 18 says we are going to have to look at this picture, okay? So remember, there's this picture here, and it looks like, actually, I'm going to stick it on here so that you can look at it. Here's a picture. Okay, I'm going to add this in. Sorry if this is taking so long. If you don't like it, you can always scroll past this. Okay. Okay, so we've got this picture here in your book, and it says find A, B, and C for the function f of x equals a sine bx plus c such that the graph matches this at the right. So a couple of things are going on here. We see that this point that they're pointing at is at negative pi over 2, comma 2. We see that right here at the top. So there's a couple things that we know. We know that the amplitude has to be 2, so that this means A is going to be 2. Now, let's see what's going on between, peaks and valleys. They're telling us the end here is 6 pi, okay? Here's what that means. See all these 1, 2, 3, 4, 5, and then 6. Each of those is pi. So this is 3 pi here and so on. Each of those little ticks on the x-axis are a value of pi, So we can see if this is sine, there's kind of been a little bit of a change, right? It's been moved over a little bit. We can see this peak here happened at negative pi over 2, which means it seems like it should have been happening over here, because in order for that to happen, for our peaks and valleys and things to be there, also this starting at 0 should have happened here. So that means everything got shifted over by pi over 2. So our shift looks like it was at a pi over 2 as well. And then we also know that, let's look at our value of how long it takes to get to the end of the period. So if we look here at, I don't know, we can look at some of these peaks and valleys and things. We can see, let's identify the same point. So I know from here to here, those are the same points. So let's count, see how many pies happen. So I see there's 1, 2, 3 full pies plus a portion of the last, which would make up a 4. So the period is 4 pi. Okay. So that means that if it's a 4 pi, that means B, so this is double the typical pi. So remember, when I multiply by 1 over B, that means whatever the B is, we take the opposite of what we see. So if we want it to double, we need B to be a half. Okay, so we end up with, and I need to fix the shift. Remember how we said the shift was a total of negative pi over 2, but remember that it had to be C over B, right? So, and actually I was premature in saying that. So if the B value is 1/2, and I don't know what the C is, so that means I know negative pi over 2 equals C, which I don't know, over B, which is 1/2. So in order to get rid of this, I'm going to multiply by 1/2 to both top and bottom, and we get C equals negative pi over 4. And that's what we've got there. So A is 2, B is 1/2, C is negative pi over 2. Okay, that was 18. Now let's do the last one, number 23. It says a plane is 64 miles north and 80 miles east of an airport. So this sounds like bearings to me. So remember, bearings are not a unit circle. Here's the airport. This is the directions north, east, south, west. And it's saying a plane is 64 miles north of the airport. So we go 64 miles north and 80 miles east of the airport. What bearing should the pilot take to directly fly? So right now, this is where the plane is at. And we need to find which way the plane should go to get directly to that point. So we're going to draw it right here, okay? So I don't need to know what's the bearing that we're looking at here. So remember, a bearing is always from the north or south line. So what we've been doing about the reference angles, about always the x-axis, get that out of your mind. The bearings always start at either the north or the south line. For us, we're closer to the north line. So we're starting at the north, and we need some sort of degree in whichever direction. So we know we're closer to the east. So this is going to be north, some degrees east. So I want to know this angle right here. Okay? So that tells me I need to find, if this is a right triangle, I'm going to use SOHCAHTOA to set up a trig function. Let's see if we can solve this. Remember, this is the opposite. Here's the hypotenuse, and here's the adjacent. So we know that the opposite is 80 and the adjacent 60. So we know the tangent, which is the opposite over the adjacent, is 80 over 64. So I want to get theta by itself, which means I'm going to take the inverse tangent of both sides. We get theta equals the inverse tangent of 80 over 64. If we plug that into your calculator, and make sure that you're, because you want this in degrees, put your mode into degrees if you haven't already. So we get inverse tangent of 80 over 64, and we get 51.34 degrees. So we say north 51.34 degrees. Okay. All right, guys, I hope that's helpful. Come see me if you